The Black Hole Survival Guide. Every decision you'd need to make. Right now, at this very moment, there's a supermassive black hole sitting at the center of our galaxy, weighing 4 million times more than our sun. And here's what keeps me awake at night. If you fell toward it, every single choice you make could mean the difference between witnessing the end of the universe or being torn apart atom by atom. This isn't science fiction. This is physics. And today, you're going to learn exactly what decisions you'd face if you found yourself approaching one of the most extreme objects in our cosmos. Welcome to your Black Hole Survival Guide. Let's set the scene. Your spacecraft has malfunctioned near a stellar mass black hole, about 10 times the mass of our sun. You're drifting closer, and your instruments are going haywire. The first decision you need to make happens right now, and it's the most critical one you'll ever face. Decision 1. Do you fire your thrusters to escape immediately, or do you take a moment to assess your situation? Here's why this matters. Black holes have a point of no return called the event horizon. Cross it, and not even light can escape. But there's another boundary you need to know about. It's called the photon sphere, located about 1.5 times the radius of the event horizon. At this distance, light itself orbits the black hole. If you're outside this region, you still have options. If you're inside it, your engines would need to propel you at speeds approaching light speed to break free. Let's say you check your instruments. You're still outside the photon sphere. Good. You have time, but not much. Your radiation detector is screaming. This brings us to Decision 2. Decision 2. Do you shield yourself from radiation using your ship's limited emergency shielding, or do you save that energy for propulsion to escape? Black holes aren't just dark, empty spaces. Matter falling into them forms an accretion disk, a swirling maelstrom of superheated gas and debris. This disk emits intense X-rays and gamma radiation. Stellar mass black holes with active accretion disks can release more energy in seconds than our sun produces in years. Your biological systems can't handle this for long. The smart choice? Activate minimal shielding and conserve fuel for escape. You'll take some radiation exposure, but you can survive it if you act fast. Speaking of fast, time itself is about to become your enemy. You notice something strange on your chronometer. It's running slower than it should compared to the signal you're receiving from Earth. This is gravitational time dilation, predicted by Einstein's general relativity. The closer you get to the black hole, the slower your clock ticks relative to the rest of the universe. Decision 3. Do you dive closer to use the black hole's gravity as a slingshot maneuver, or do you take the longer, safer route away from it? This is called a gravitational assist, and we've used it with planets for decades. But with a black hole, the stakes are infinitely higher. If you calculate it perfectly, you could use the intense gravity to accelerate your ship without using fuel, flinging yourself away at tremendous speed. The math has to be absolutely perfect. Too close, and you'll cross the event horizon. Too far, and you won't gain enough velocity to escape the region. Let's say you're a calculated risk taker. You plot a course that brings you closer, just outside the innermost stable circular orbit. This is the closest distance where matter can orbit a black hole without spiraling inward. For a non-rotating black hole, this is 3 times the radius of the event horizon. As you execute the maneuver, your ship shudders. You're experiencing spaghettification at its earliest stages. Decision 4 is upon you. Decision 4. Do you orient your ship perpendicular to the black hole or parallel to it? Spaghettification, also called the tidal effect, occurs because gravity is stronger on the side of your ship closer to the black hole than the side farther away. If you're oriented perpendicular, with your head pointing toward the black hole, the difference in gravitational force between your head and feet becomes extreme. For a stellar mass black hole, you'd feel this difference much sooner than with a supermassive black hole. Orient your ship parallel to minimize the differential. Every meter counts now. Your gravitational assist is working. You're accelerating, but something incredible is happening outside your window. The stars are behaving strangely. Light from stars behind the black hole is bending around it, creating a perfect ring of light called an Einstein ring. The black hole is acting as a gravitational lens, warping space-time itself. But there's something else. You're seeing light from stars that should be behind you appearing in front of you. The black hole's gravity is so strong it's bending light from all directions around it. You're witnessing the photon sphere in action, where light rays orbit the black hole multiple times before escaping. Your course is set, but now you face Decision 5. Decision 5. Do you look back at the black hole through your observation equipment, or do you focus solely on your escape trajectory? Here's the dilemma. If you look back, you might observe one of the most spectacular phenomena in physics. As you accelerate away, due to relativistic effects and gravitational lensing, you could potentially see highly distorted images of the entire history of matter falling into the black hole, compressed and blue shifted into a brilliant display. This data would be invaluable to science. But observation takes attention and system resources. Your navigation requires precision. One course correction missed could send you tumbling back. You decide to let your automated systems record while you focus on flying. Good call. Your ship's velocity is increasing. You're approaching 10% the speed of light. At these speeds, relativistic effects are becoming noticeable. Your mass is increasing from your perspective, though infinitesimally. Time for Decision 6. Decision 6. Do you continue accelerating away at maximum thrust, or do you cut engines and coast to conserve fuel for later course corrections? You're far enough from the photon sphere now that escape is almost certain, but you're not out of danger yet. The black hole exists in a neighborhood, and that neighborhood might contain other hazards. Rogue planets, asteroid fields, or even a companion star in a binary system. Conservation might be wise. You cut to minimal thrust, maintaining trajectory. Your radiation exposure is dropping. The accretion disk is no longer visible as a bright ring, but as a fading glow behind you. Then your long-range sensors detect something. There's a debris field ahead, likely remnants of previous visitors who weren't as fortunate. Decision 7 emerges. Decision 7. Do you navigate through the debris field using your depleted fuel reserves, or do you risk a longer trajectory around it with uncertain gravitational influences from nearby objects? Debris fields near black holes are unpredictable. Objects can be moving at significant fractions of light speed, accelerated by previous close encounters. A collision with even a small object at these velocities would be catastrophic. Your shielding is already compromised from radiation exposure. You plot a course around. It adds 30 minutes to your escape time, but you'll arrive alive. As you clear the danger zone, you notice your chronometer again. Compared to Earth time, you've experienced time dilation of approximately 47 minutes. While several hours passed on Earth, you experienced less time. Your journey near the black hole has literally taken you into the future. Decision 8 arrives with a message from your home base. Decision 8. Do you transmit your scientific data immediately while it's fresh, risking signal interception by other interests, or do you wait until you're in a secure location? The data you've collected includes direct observations of space-time curvature, measurements of Hawking radiation effects if you got close enough, and recordings of relativistic phenomena that few humans have witnessed. This information could revolutionize our understanding of physics. But in this scenario, other factions might want this data for themselves, perhaps to weaponize black hole research or to monopolize the knowledge. You encrypt and burst transmit the essentials, keeping the detailed analysis for secure delivery. Survival and science can coexist. You're now at a safe distance, but you're not heading home yet. Your fuel is nearly depleted. Decision 9 confronts you. Decision 9. Do you signal for rescue and wait, conserving all remaining resources, or do you attempt to reach the nearest outpost under your own power? Signaling for rescue means potentially waiting days in the cold of space. Your life support is damaged. You have maybe 72 hours of breathable air. The nearest outpost is 60 hours away at your current speed, but you'd arrive with zero fuel and no margin for error. You run the calculations 3 times. Each time, they say the same thing. You can make it, but barely. You commit. Full burn toward the outpost. 50 hours later, you're on fumes. The outpost appears on visual sensors. You've made it, but there's one final decision, Decision 10. Decision 10. Do you broadcast your approach openly, identifying yourself and your emergency, or do you maintain radio silence until you can visually confirm the outpost is safe? In deep space, not every outpost is friendly. Some are automated. Some are abandoned. Some have been taken over by salvagers or worse. Your weakened state makes you vulnerable. You send a tight beam communication, just enough to identify yourself to the outpost's AI without broadcasting to the whole sector. Smart. The outpost acknowledges. Docking permission granted. You guide your battered ship into the hangar with the last reserves of your maneuvering thrusters. As the airlock seals and atmosphere floods the chamber, you finally exhale. You survived a black hole encounter. But let's talk about what you really learned, because this journey teaches us something profound about our universe. Black holes aren't just cosmic vacuum cleaners or science fiction monsters. They're laboratories where the laws of physics are pushed to their absolute limits. They teach us about gravity, time, light, and the very fabric of reality. Every decision you made was rooted in real physics. Gravitational time dilation isn't theoretical. We measure it with atomic clocks on Earth versus satellites in orbit. Spaghettification is the inevitable result of tidal forces that exist anywhere gravity has a gradient. The photon sphere, the event horizon, the accretion disk, all of these are predicted by equations and confirmed by observations of real black holes like Sagittarius A star at our galaxy's center, or the supermassive black hole in M87 that we finally photographed in 2019. That image, by the way, showed us the shadow of a black hole for the first time, confirming that the event horizon exists exactly where Einstein's equations predicted it would be, over a century after he published his theory. Here's what's truly mind-bending. If you actually fell into a black hole past the event horizon, from your perspective, nothing dramatic would happen at that exact moment. You wouldn't see a barrier or feel a jolt. You'd simply continue falling. But to an observer watching you from a safe distance, they would never see you cross the horizon. Due to time dilation, you would appear to slow down, freeze, and fade away as the light from your body becomes increasingly red-shifted until it disappears entirely. You'd be frozen at the edge of the black hole forever from their perspective, while from your perspective, you'd cross in finite time and meet your end at the singularity. Two perspectives, two completely different experiences of the same event. That's relativity. And what about inside? Beyond the event horizon, space and time swap roles. Just as you can't avoid moving forward in time outside the black hole, inside, you can't avoid moving toward the singularity. It's not a place in space anymore. It's a moment in time. Your future. Inevitable. At the singularity itself, density becomes infinite, space-time curvature becomes infinite, and our equations break down. We simply don't know what happens there. Quantum mechanics and general relativity, our two most successful theories, give different, incompatible answers. This is where physicists hope a theory of quantum gravity will finally illuminate the darkness. But maybe you're wondering, could we ever actually travel near a black hole? With current technology, no. The nearest known black hole is about 1,500 light-years away. But supermassive black holes, the giants at the centers of galaxies, offer a strange possibility. Because they're so massive, their event horizons are enormous, and the tidal forces at the event horizon are actually much weaker than those of stellar mass black holes. You could, in theory, cross the event horizon of a supermassive black hole and survive for minutes or even hours before spaghettification destroyed you deeper inside. Of course, you could never report back what you found. Some physicists have speculated about even stranger possibilities. Rotating black holes, described by the Kerr metric, have an inner structure different from non-rotating ones. They have an inner horizon and a ring singularity, rather than a point singularity. Mathematically, the equations suggest you could pass through the ring and emerge into another region of space-time, perhaps another universe. But the trip would likely involve infinite tidal forces and infinite blue-shifted radiation that would destroy anything attempting the journey. Still, the mathematics allows it, and that's fascinating. Your journey today was about survival, but it was also about wonder. Black holes remind us that the universe is far stranger and more beautiful than our everyday experience suggests. They're not just objects to fear. They're invitations to understand the cosmos at its most extreme. Every black hole was born from the death of a massive star, a supernova that compressed matter beyond the point where atomic structure could resist. They're recycling centers for the universe, and some theories suggest they might even be birthplaces for new universes through processes we can barely imagine. So what's the real survival guide for black holes? It's this: respect the physics, understand your boundaries, make informed decisions, and never underestimate the power of gravity. Whether you're navigating space-time or navigating life, those principles serve you well. Thanks for taking this journey with me today. If you survived this guide, you're ready for anything the cosmos might throw at you. Until next time, keep looking up, keep questioning, and keep exploring the magnificent universe we call home.